So let us see how to find the eigenvalues and eigenvectors of a matrix. Okay, so eigenvalues and eigenvectors of a matrix. So what is the eigenvalue of a matrix? So for example, I have the matrix A. Okay, suppose 4, 2, 1, 3 into I am taking the vector 1, comma 0. So this will be equal to 4 and 1, right? This is equal to direct multiplication. 4 into 4 plus 2 into 0, and another one is 1 into 1 plus 3 into 0. So this is equal to I cannot write as lambda times x, but if I have the matrix 4, 2, 0, 0, 1, comma 0, which is equal to what I will get is 4, 0. So this is equal to 4 times 1, comma 0, right? So what is the meaning here? Suppose I have the vector x is equal to 1, comma 0. The first matrix 4, 2, 1, 3 does not provide some lambda times x, but in the second case the matrix 4, 2, 0, 0 provide some lambda times x, that is this is lambda, here lambda is 4, 4 into x is 1, comma 0, right? Lambda times x. So the second matrix transforms the given vector 1, comma 0 into some other vector which is a multiple of the same vector, that is a parallel vector. 4, comma 0 is a parallel vector to 1, comma 0, right? So this matrix, this 4, 2, 0, 0 transforms the given vector 1, comma 0 into 4, comma 0, but in case of first one 4, 2, 1, 3 does not provide does not transform the vector 1, comma 0 into the some other vector which is parallel to 1, comma 0, right? First case does not be a eigenvector. So here this lambda is called the eigenvalue of this matrix A, and the corresponding vector is called the eigenvector of this matrix A. Is it right? So here lambda equal to 4 is the eigenvalue. Lambda is the 4 is the eigenvalue of A equal to 4, 2, 0, 0, and 1, comma 0 is the eigenvector for the matrix A is equal to 4 to 0, 0. But in the first case, in this case, this we cannot transform any lambda times x. Therefore, this 1, comma 0 is not a eigenvector. Okay. So this is a basic idea. That means, suppose we have the vector 1, comma 0. It transforms to some other vector 4, comma 0 or parallel to some other vector. Okay, for example it may be 6, comma 0 or 8, comma 0 or it is 12, comma 0, like that. It may be anything, but it should be parallel to the given vector. Then only we can say that the given matrix transforms the vector to lambda times x, and also the vector is called the eigenvector of the matrix. Is it right? So that's it. So now let us see some example how to evaluate this eigenvalue and eigenvector. Okay, so I am taking the matrix A is equal to 1, 3, 2, 6. Find eigenvalues and eigenvectors. Find eigenvalues and eigenvectors. So see, so what is the condition? This A transforms this vector into lambda times x. This is the condition, right? For if x is a eigenvector for A na, this satisfies the condition Ax is equal to lambda times x. Then this lambda is eigenvalue and x is the eigenvector of a matrix A. So this implies what I can say, Ax minus lambda x is equal to 0, right? So this implies what I can write, A minus lambda times I identity matrix in into x is equal to 0. Here this x is never be 0. Eigenvector cannot be 0. Therefore, because we should take the vector which is non-zero. Okay, va? So here this implies what I will get, a minus lambda I is equal to 0. So this implies determinant of a minus lambda I equal to 0. So this is a characteristic equation for the matrix A. Okay. So now let us discuss this for this examples. So A equal to 1, 3, 2, 6. So what is characteristic equation? A minus lambda I, determinant of lambda A minus lambda equal to 0. So what is A minus lambda I? A is a matrix. A minus lambda I equal to A is 1, 3, 2, 6 minus lambda times I is the matrix 1, 0, 0, 1. So which is equal to 1, 3, 2, 6 minus lambda 0, 0, lambda. So which is equal to 1 minus lambda 3, 2, 6 minus lambda. So only diagonal entries will be changed, right? In A, just we need to subtract lambda from the diagonal elements. So simply I can write it as 1 minus lambda, 6 minus lambda, 3, 2. So diagonal entries only will be changed. Remaining entries we can keep it as it is, right? So this equal to 0. So now what is the determinant? 1 minus lambda into 6 minus lambda minus 6 is equal to 0. So this is 6 minus lambda minus 6 lambda plus lambda square minus 6 is equal to 0. Simplification, 6 minus lambda minus lambda, so totally it is 7 lambda plus lambda square minus 6 is equal to 0. So this will be lambda square minus 7 lambda is equal to 0. So lambda into lambda minus 7 is equal to 0. So lambda equal to 0 comma 7. So these two are the eigenvalues of a given matrix. Okay. So now how to find the eigenvector, corresponding eigenvector. So now we have the two eigenvalues, lambda equal to 0 comma 7. So our matrix is A is equal to 1, 3, 2, 6. Okay. So now if lambda equal to 0, first case, to find eigenvector, first case, lambda equal to 0, if I assume that the equation is A minus lambda I into x is equal to 0. This is our equation, right? So from this equation only we have to find this eigenvector, right? So A minus lambda into x is equal to 0. So here I am taking x is equal to some x1, x2 because it is a 2 cross 2 matrix. So you can assume any arbitrary vector. Instead of x1, x2 you can assume y1, y2 or some other variables, right? So A minus lambda I, what is A minus lambda I? Just 1 minus lambda, 6 minus lambda, 3, 2 into x1, x2 equal to 0, 0. Okay. So lambda equal to 0. If I put lambda equal to 0, in the first case lambda equal to 0. If I put lambda equal to 0, then this will become 1, 3, 2, 6 into x1, x2 equal to 0. So now multiply this with this. You will get x1 plus 2, 3x2 is equal to 0. Second equation is 2x1 plus 6x2 is equal to 0. If you simplify this equation, you will get the same equation, x1 plus 3x2 equal to 0. So now we have only one equation, that is x1 plus 3x2 is equal to 0, but we have two unknowns. Therefore the system has infinite number of solutions, right? The system has infinite number of solution. So we should take only one non-zero solution. Okay, so we never take the solution 0, 0 because obviously in this case if you put x1 0, x2 0, this will be 0. but that is a solution, but we never need a solution, never need a zero solution. So we only need a non-zero solution. So you have to assume some other non-zero solution. So from this, what I can write, x1 is equal to minus 3x2. If you put x2 is equal to k, then what about x1, x2 is equal to, x2 is k, x1 value is minus 3k, where k belongs to R. So we have infinite number of solution, but in this I can take only one solution. If you take k outside, it is minus 3, 1. So x1 you can assume that only minus 3, 1. So this is the eigenvector corresponding to the lambda equal to 0. Okay, va? So you can assume k into minus 3, 1, k equal to 2 enagum. This will happen k into minus a, k equal to 2 na minus 6 comma 2, that is also a solution. If you k equal to 3, if you assume k equal to 3, 3 into minus 3 is minus 3, now 1, minus 3 into 3, 1 into 3, that is minus 9, 3, that is also a solution. So we have infinite number of solutions. Among them we should take only one non-zero solution. Okay. So next case, lambda equal to 7. Second case is lambda equal to 7. Our matrix is A minus A equal to 1, 3, 2, 6. What is A minus lambda I into x is equal to 0? So 1 minus 7, 3, 2, 6 minus 7. So here lambda is 7 into x1, x2 equal to 0, 0. So this will be minus 6, 3, 2, minus 1, right? Into x1, x2 equal to 0. From the first row, 6x1 minus 6x1 plus 3x2 equal to 0. Second row, 2x1 plus minus 3x2 is equal to 0. So this equation also minus 2x1 minus 2x1 plus x2 equal to 0. Second equation is here minus x2, right? So this and this are same, right? Same equation. This multiply, if you multiply this equation with the minus, then you will get this equation, right? The both equations are same. So we have again only one equation, that is 2x1 minus x2 is equal to 0. So 2x1 is equal to x2. So again if you put x2 is equal to k, let us assume x2 is equal to k, where k belongs to R, then what about x1, x2? x2 value is k, then x1 value is from here k by 2, right? Where k belongs to R. So here 1 by 2 comma 1 is a vector corresponding to eigenvalue lambda equal to 7. Is it clear? So that's it. So now we have the vector lambda equal to 0. We have the eigenvector. What is eigenvector? That is minus 3 comma 1. x1 is equal to minus 3 comma 1, and for lambda is equal to 7, the eigenvector x2 is 1 by 2 comma 1. Okay. So this multiples of this vector also a eigenvector. For example, you can assume minus 6 comma 2, that is also a solution, therefore it is also a eigenvector. Minus 9 comma 3, which is also a solution. Here in this case you can multiply with the 2, what will get 1 and 2. So this is also a eigenvector for the eigenvalue lambda. Or if you multiply with the 4, you will get a 2, 4, that is also a solution. So you have infinite number of solution. Among them we need only one solution, which is non-zero. Okay. So this is okay. So we have A is equal to, we have discussed the problem 1, 3, 2, 6. So there is a characteristic equation A minus lambda I into X equal to 0. That is a characteristic equation. So instead of this finding determinant value, we can use some other formula. That is lambda square minus S1 lambda plus S2 equal to 0. This is a simplified form. Compare with this determinant form. So here what is S1? S1 is equal to trace of A. Trace of the matrix A. So trace is nothing but sum of the diagonal elements, that is 1 plus 6 is equal to 7. Sum of the diagonal elements. 1 and 6 are the diagonal elements. S2 is equal to determinant of A. So which is equal to 6 minus 6, which is 0. Therefore this characteristic equation become lambda square minus 7 lambda equal to 0. So lambda into lambda minus 7 is equal to 0. So we have the eigenvalues lambda equal to 0 comma 7. That's it. Is it clear? So instead of this determinant of A minus lambda equal to 0, we can use the form, simplified form, lambda square minus S1 lambda plus S2 equal to 0. So this is for a 2 cross 2 matrix. What about 3 cross 3 matrix? For a 3 cross 3 matrix, we can use the characteristic equation A minus lambda equal to 0, A minus lambda equal to 0, or lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0, where S1 is equal to again trace of A, sum of the diagonal elements, S2 is equal to sum of the determinants of minors of A, determinants of minors of A. What is sum of the I will discuss, we will discuss what is it. And S3 is equal to determinant of A. So for example, we have the matrix 1 2 3 0 1 2 0 0 2. Okay, so this is a example. Suppose trace of A, what is trace of A? S1 is equal to 1 plus 1 plus 2, that is 4. What is S2? So you have to consider minors of diagonal elements, that is 1 is the first diagonal element, corresponding minor is 1 2 0 2, right? 1 is the first minor, corresponding minor is 1 2 0 2. Next diagonal element is 1, this one. What is the minor matrix? 1 3 0 2, right? So 1 3 0 2 plus, what is the third diagonal element? 2. So corresponding minor matrix is 1 2 0 1, right? 1 2 0 1. So this is a S2 value. So you can find it now. So 2 minus 0, second one 2 minus 0, and third one 1 minus 0. So which is equal to 2 plus 1, which is equal to 5. So this is S2 value. So S3 is a determinant A. Already you know how to evaluate the determinant. So you can evaluate it, right? So this is the way to find the characteristic equation for the 3 cross 3 matrix. Okay. So what is determinant A here? Determinant A is so just we have first with the first row you can express it, right? So 1 into 2 minus 0, 1 into 2, so 2 minus 0, that is 2. So the equation is lambda cube minus S1 value is 4, 4 lambda square plus S2 value is 5 lambda minus S3 value is 2 equal to 0. So this is the characteristic equation for this matrix. So that's it. Thank you for watching. In the next video, I will explain how to evaluate the eigenvalues and eigenvectors for a 3 cross 3 matrix. Thank you for watching and keep supporting me.